Hello everyone, welcome again to Modeling Methods in ME and Mechanical Engineering, and today we're going to discuss the concept of the curl of a vector field. And this is another vector operator that applies to fields, and it has a completely different physical meaning, which we'll try to explain today, as well as the mathematical construct of it. So, modeling methods in ME. So we'll talk about the curl of a vector field. So this applies only to vector fields and not to scalar fields. So such as a divergency, for example, you can only take the divergency of a vector field or a tensor field, not a scalar. Now the curl of V, a vector field V, is given by the limit when the region of space goes to 0, 1 divided by that region of space, which can be volume or an area, depending on the number of dimensions you're working on, times the integral over the surface of the normal vector crossed into the vector field, the gamma. Okay. Now this is slightly different from the definition of a divergency, because in the case of the divergency it was v dot n. Now we have n cross v. Instead of having the scalar product, now we have the cross product or vector product. So this goes like this. So let's assume that we have a region in space, again, that we denote as gamma, whose surface is denoted, the region is denoted as omega, whose surface is denoted as gamma. And let's say that we have a field traversing space, and this field is V. Again, it's a vector field, that's why there's arrows attached to this. And at some portion of the boundary, again, this is d gamma, we have a normal vector that points always outside. By convention, we define the normal vector as pointing outward. And what we're basically doing is taking the cross product of n cross v, and let's try to analyze what that is. If you remember from your calculus 3, the cross product of two vectors vanishes when the two vectors are parallel to each other, and it maximizes when the two vectors are perpendicular to each other. So essentially, if the vector field V is actually flowing perpendicularly to that section of the surface, perpendicularly, it's just escaping through there, where the divergency, where the v dot n will be maximum, the n cross v will be minimum, it will be 0. And in the event that at that particular window or piece of the boundary, the vector field is actually traversing perfectly tangential, parallel to the normal vector, then that will be maximum. In essence, this particular product, or the magnitude of the product of vector A cross a vector B is equal to the magnitude of A times the magnitude of B times the sine in this case, because it's maximum at 90 degrees when the two are perpendicular to each other, the sine of the angle that separates the two. All right, so let's recall a couple of other vector identities. One that says that A, which is AX plus BX, AY in the Y direction, plus AZ in the Z direction. And let's say B is equal to BX in the X direction, plus BY in the Y direction, plus BZ in the Z direction. So this is AY. We define the cross product of these two vectors as another vector. So the cross product is a vector operation. So the result of the cross product between two vectors is another vector. And we can attain these by simply writing the two vectors in this matrix form, where the components of A will go first, the components of B will go second. And then some people augment this vertically. I like to augment it in the X direction. So you basically repeat the first two columns. That means augmenting the matrix horizontally. And then what you do is you multiply the diagonals and then multiply the counter diagonals, but those go negative. So the diagonal multiplications are positive and the counter diagonal multiplications are negative. So A cross B is, well, AY times BC in the X direction, AY times BZ in the X direction, plus AZ BX, AZ BX in the Y direction, plus AX BY in the Z direction. And then the negative of these ones, this would be AX BZ in the Y direction, minus AZ BY in the X direction, minus AY BX in the Z direction. And then we can just group them. And it would be AY BZ minus AZ BY in the X direction, plus AZ BX minus AX BZ in the Y direction. Let me squeeze this one here in this little space. Actually, I can do it here. Plus AX BY minus AY BX in the Z direction. So these are the three components of the cross product between two vectors. All right, so let me move to the next page. All right, so one thing to note immediately is that the product of A and B is not equal to the product of B and A. In fact, A cross B is equal to the negative of B cross A. So this means that this operation is anti-commutative. This is negative of the commutative theory or property. Now the two vectors that we're working with and the curl are V, which remember we usually use AX, VEY, WEZ, and N, for which we use NX in the X direction, plus NY in the Y direction, plus NZ in the Z direction. So each of these vectors have three components. And for the purpose of this demonstration of coming up with what the curl of the vector V will turn out to be in terms of a vector operation, I'm going to express V as V dot EX in the X direction, plus V dot EY in the Y direction, plus V dot EZ in the Z direction. Okay, this is also true. This will bring you back to U, V, and W, and correspond to this. And I'm going to express N cross V as N crossed into this whole thing. V dot X or EX in the X direction, plus V dot EY in the Y direction, plus V dot EZ in the Z direction. All right, and we're going to use a vector identity. A vector identity that reads A dotted into B cross C is equal to A crossed into B dotted into C. It's a very simple vector identity. You can check it that it works, but we're not going to go through the demonstration that that's true. Just take my word for it. So n cross v, I'm going to take this form up here, and I'm going to modify it slightly to show that this is n dot v cross ex in the x direction plus n dot v cross ey in the y direction plus n dotted into v cross ez in the z direction. Okay, same thing. So what I'm going to do is I'm going to plug this back into the definition of curl. So the curl of vector v is the limit when omega goes to 0 of 1 over omega, open brackets, and then I'm going to separate these into this original definition of the curl. This one, I'm going to separate it into 3 different integrals because I'm going to separate n cross v into 3 different terms. So the first one is going to be the integral of n dotted into v cross ex, and all of these goes in the x direction, plus the integral n dotted into v cross ey, the gamma, in the y direction, plus the integral of gamma, or over gamma, of n dotted into v cross ez in the z direction. There we go. Now the reason I'm doing this is, well, because I know exactly what this is. This integral right here corresponds to the divergency of this vector right here. The limit when omega goes to 0 divided times 1 over omega of the integral over the boundary surrounding omega of n dot vector, or vector dot n, which is the same thing, is the divergency of these vector in parentheses. So basically we have the sum of 3 divergences here. So what I'm going to do is I'm going to transform these integrals, which are boundary integrals. I'm going to need a new page for that. This is not going to fit here. I'm going to use the Gauss divergency theorem to I'm going to say using Gauss's divergency theorem, or there's a couple ways to do this. I can just simply say that this is the divergency of this vector, this is the divergency of this vector, and this is the divergency of this vector. Or I can simply use the Gauss divergency theorem. Whichever way you prefer, it will work out to say that this is the limit when omega goes to 0, 1 over omega, and I can turn this boundary integral into a domain integral of the divergency of v cross ex d omega in the x direction, plus an integral over the domain of the divergency of v cross ey d omega in the y direction, plus integral over the domain v cross ez d omega in the z direction. And close the keys. All right. So then I can cancel the limit when omega goes to 0 of the integral of omega. I can just simply use the integrand. It's exactly the same thing. So the curl of v will simply come down or boil down to be the divergency of v cross EX in the X direction plus the divergency of V cross EY in the Y direction plus the divergency of V cross EZ in the Z direction. So I'm looking at the three terms now, and now I have a vector operation, but I can further reduce that vector operation because it's kind of exceedingly complex at this point, because you have to do a cross product and a dot product in order to get each of the three components. So I can recognize, for example, this first operation here, V cross EX. So how do I perform the cross product of these two vectors? Again, I do EX, EY, EZ, the three components of V, which is U, V, and W, and the three components of EX, which is 1, 0, 0. And then I augment this matrix, U1, V0, and then I calculate the determinant of these, which is multiply the diagonals and then subtract the multiplication of the counter diagonals in order to arrive at V cross EX equals W. See, a lot of these will go to 0, and the only ones that survive are W times EY minus V times EZ. There you have it. And furthermore, now I need to take the divergency of these. So the divergency of V cross EX, which is a scalar operation. So I'm going to take this, which is a vector, and take the divergency of that is, well, I'm going to do it in two steps here. The divergency will just simply be this operator dotted into this vector, which is, well, 0 and EX, W and EY, minus V and EZ. So the derivative of 0 is 0, the derivative of W with respect to Y, minus the derivative of V with respect to C. So the divergency of V cross EX goes as dW dy minus dV dz. Okay, and that's a scalar because I'm taking the divergency of a vector, so that's a scalar. But that will be plugged in back into the form of the curl, which, well, this is one of the components of the resulting vector. We can do this similarly for these vector, find the cross product between these two, take the divergency of that, and what will happen, let me go to the next slide. What will happen, as expected, is that these three vectors, so similarly, these vector here results in du dz minus dw dx, and this one results in dv dx minus du dy. All right, so then I can take these three, plug them into right here, and I have my three components for the curl of the vector v. So the curl of v is therefore dw dy minus dv dz, and the x direction, let me see if I can fit them all here, du dz minus dw dx, and the y direction plus dv dx minus du dy in the z direction. So that's the curl operator. Given a vector UVW, and where each of these components of these vector field are functions themselves, this is the resulting vector field that is the curl of the vector. Now, one particular aspect of these that we can recognize right away is that, well, maybe not right away, after inspection, we could recognize that this resulting form is perfectly equivalent to crossing nabla with V. So, and that's why the curl of a vector field is usually denoted as nabla cross V. All right, so let's show that. Let's show that this is indeed the same thing that we just did over this long demonstration. So nabla cross V, in that order, is the cross product between these two vectors, where nabla is dx, dy, dz, and V is UVW. And again, I am going to augment this matrix with the first two columns, and I am going to take the determinant of this augmented matrix by multiplying the diagonals and the off diagonal, the counter diagonals. So you can see that this will be the w dy and the x direction plus du dz and the y direction plus dv dx and the z direction. Those are the positive ones. And then coming back, this will be minus dw dx in the y direction minus dv dz in the x direction minus du dy in the z direction. And when you combine these together, you'll get the w dy minus dv dz in the x direction, and then you get du dz minus the w dx in the y direction, and then you get dv dx minus du dy in the z direction, which is identical to what we did up here. So the curl of V is the same thing as del cross V. So indeed, del cross V is equivalent to curl of V. So now we have a fourth vector field operator. We had the gradient that applies to scalars, also applies to vector fields, but it turns them into a tensor, which we don't know what they are yet. We have a divergency, which will take a vector field and turn it into a scalar. We have the Laplace, which is a combination of the divergency and the gradient. This is divergency of the gradient of a scalar. And now we have the curl. But what does this mean? What does the curl mean? Well, we had a reasonable physical explanation for the divergency. We took it from the definition and that illustration that we made. And we should have one for the curl too. Remember the divergency, when we have v dot n, that's basically quantifying the amount of stuff that goes in and out of the domain, or out minus in of the domain. Because remember, if you assume v, this vector field is a velocity field, it can be anything, it can be a force field or anything else, but assume that it's a velocity field, and then you have velocity times area, that gives you flow rate, and then the integral over the entire surface is a summation over all the flow rates that go out minus the ones that go in. If the divergency is equal to 0, it means that there's no compliance, there's no compressibility of the flow field within that region. Now the curl is a different story, because now we're crossing n into v, and remember that the cross product of n and v is maximum when the two vectors are perpendicular to each other, like it basically shows here in this illustration by chance. So when that particular product is maximum, this integral will be maximum. So if you think about this is sort of the opposite of things entering and leaving the domain. It would be things actually slipping around the domain. And the term slipping might be an incorrect one here, because this is not technically what it does. What it technically does is basically takes that domain and applies angular momentum to it. And that's why we call this a curl, because it basically curls the domain. The measure of curl of a vector field, if a vector field has zero curl, it means that the vector field is essentially not imposing any angular momentum over the domain. That's one way of looking at it. And a maximum curl or a large curl means exactly the opposite. That's from the mathematical point. We're trying to make a bridge between the mathematical formulation and the physical interpretation of this one. Let me try to put that in words. So what happens is the curl of a vector field is a measure of rotation of the field at a point, at the point where the curl is evaluated. That can be another physical interpretation for these. So again, let's assume that this vector field is a fluid flow. It's a flow field, a velocity field. So in fluids, let's say that you have this field doing this. So that's V, right? So it's kind of moving up and down, sort of like rotating around things or circulating, let's say circulation. And then if you look at this particular streamline and you draw a fluid particle there that you try to track, and then you probably notice that that fluid particle tends to rotate about its own axis with respect to the streamline. Again, this is a physical interpretation of the curl in fluid flows, although the curl not only appears in fluid flow equations, it appears in electromagnetics, it appears everywhere. So if there is some angular motion, the curl of this vector field is different than zero. If the fluid particles along each of the streamlines appear to be rotating about their own axis, then the curl of that vector field will be different than zero. So conversely, if the fluid particles actually appear to be always aligned the same exact way with respect to the streamline about their own axis, then the curl of a vector field is zero. Now, that's an interpretation. Okay. Now, when I say curl, I don't mean circulation. You can have a vector field, you can have a velocity field that is highly circulating, that is circulating around this room, for example, and you can measure it. And when you go and calculate the curl of that vector field, you might end up zero. In fact, in ideal fluid flows, you can actually, which are based on irrotational flows, you can exemplify the vector field of a tornado, for example. And a tornado is highly circulating, however, it's non-rotating. So you can have a flow field circulate around, but the fluid particles are not rotating about their own axis. They don't have angular momentum with regards to their own, or with respect to their own axis. Now, a very useful identity, and this is just a mathematical identity, is that the curl of the gradient of a scalar potential field is equal to 0, always. So if you take the gradient of phi, and then to that resulting vector field you take the curl, you will always get 0, no matter what. Okay, so this is very useful for one particular reason. So this implies that if a given velocity field v, or vector field for that matter, is curl free or irrotational, so we call fields that have 0 curl, we call them irrotational. That means curl free everywhere, not just at a single point, but when you take the curl of a vector field, it happens to be 0 everywhere. And by the way, technically the right way of writing this would be 0 ex, 0 ey, 0 ec, because remember that the vector product or the curl operation is a vector operation, and you should end up with 3 components. So if all 3 components are 0 everywhere, then because of this identity here, there must exist a potential field phi such that v is equal to the grad of phi, or v is equal to negative of the grad of phi. It will work exactly the same way. In fact, it will work exactly the same way if you had a constant, so it's proportional to the grad of phi. Okay, so that happens because of this particular identity. So again, if it happens that you are given a velocity field that resolves to irrotationality, that is curl free everywhere, then there must exist a potential field, a potential scalar field, that from which you can derive the velocity, just like that. And that's because these particular. So we call this is the velocity potential. It's the velocity potential. All right, so let's look at a quick example here. The velocity potential. And by the way, it's just the potential, because V doesn't have to be a velocity. It can be an electric field, it can be a magnetic field, it can be a force field, and there's an underlying potential from which you can derive that field, and it's only true if the field is curl free or irrotational. By the way, the word irrotationality, curl free, is also used interchangeably with the word conservative. If the field is conservative, it means that the curl is 0, or you have 0 rotation. So, example. Let's assume that we are given this velocity potential, or the potential, we don't have to call it velocity potential again, and it happens to be xyz. We can take the gradient of this velocity potential, and it will turn out to be yz in the x direction plus xz in the y direction plus xy in the z direction. And now let's try to take, so this is the gradient of this field. Let's try to take the curl of this gradient. and we should get 0, right? According to this mathematical identity, regardless of what this function is, you can just come up with your own function, make it as complicated as you want. But if you take the gradient of that function, you end up with this vector field. And now if you take the curl of that, you'll have to do this. So the first dy ddz, and then this will be yz, xz, xy, and let's augment this, ex, yz, ey, xz. And we'll take that. Basically, we're taking the determinant of these matrix, calculating the determinant of this original matrix, and we do so by augmenting it. So we have d dy of xy, d dy of xy, that's in the x direction. In the negative x direction, we have minus d dz of xz. That goes in the x direction. Plus, in the y direction, we have d dz of yz. And in the negative y direction, we have d dx of xy. And finally, in the positive z direction, we have d dx of xz, minus in the negative z direction, we have d dy of yz. All right, so the curl of the gradient of this particular phi, this basically doesn't prove the theorem for all possible potential functions phi. It proves it for this particular one, but we can do this in general by saying that phi is just any function, and then calculate the gradient of that function, plug it in here, and then end up with all these quantities, and you'll notice that they'll cancel out. So here you have the d dy of xy is x, d dz of xz is minus x in the x direction, plus d dz of yz is y, and d dx of xy is y, plus d dx of xz is z, and d dy of yz is z. And as you can see, this resolves to 0 in the x direction, plus 0 in the y direction, plus 0 in the z direction. It's not a coincidence, but you'll always get a 0. Furthermore, you can say that if this is a vector field, this is a velocity potential, then this is a velocity. This velocity field is curl free. You just demonstrated that. And because if I had given you this as the velocity field, so let me show you that aspect of these. If I have given you this problem in the opposite direction, if I had given you v is equal to yz in the x direction, plus xz in the y direction, plus xy in the z direction, and then you happen to calculate, the curl of v, and you show that it's equal to 0, then there must exist phi such that phi comes from the grad of phi. Okay, now let's find that phi. So if phi comes from the grad of phi, then v is equal to the phi dx in the x direction, plus d phi dy in the y direction plus d phi dz in the z direction. So it looks like we have three equations right there. So if we make this one equal to this one, we notice that d phi dx has to be equal to yz, d phi dy has to be equal to xz in this particular case, and d phi dz has to be equal to xy. So then we can calculate phi by integrating yz as a function of x. We can also calculate phi by integrating xz as a function of y, and we can calculate phi by integrating xy as a function of z. So three separate ways of getting to phi, and by the way, these are not three different results. All three of these have to coincide simultaneously. What is the integral of yz as a function of x? These are constants, right? This is an integration with respect to x. This will be xyc, right? Plus a function of y plus a function of z. Why there would be a function of y and a function of z? Because those could be constants of integration. I assume that these are, because y and z are constants, we can end up with a function of y and a function of c that could potentially be functions, constants of integration in this particular integral. Because if you differentiate these with respect to x, you'll get yz, this one will go to 0, and this one will go to 0. A partial derivative of these with respect to x will eliminate this one and this one. Likewise here, the integral of xz with respect to y, x and z are constant, you can take them out of the integral, so you'll get xyz. Plus a function of x and a function of z. Well, we don't need to call them f and g, we can call them h and p or whatever, but you get my point. These are constants of integration, or potential constants of integration. And here the integral of xy with respect to c will be xyz, plus a function of x and a function of y, who could potentially be constants of integration. Again, these are not three different solutions to the same problem. These solutions have to coincide, otherwise you did something wrong. Either the curl is not 0, so this function doesn't exist, or we did something wrong in the integral. So for these to be true, any function of x, y, and z has to appear in all three integrals, right here and right here. And any function of only x, only y, only xy, only xz, and only yz have to appear somewhere in the other integral. So for example, a function of y would have to show up here, and a function of z would have to show up here. A function of x will have to show up here, and a function of y would have to show up here, and so on and so forth. So additional terms that are not composed terms of all independent quantities or independent variables will show up in the other integrals. So in this case, because none of these appear in the other integrals, this has to be 0, 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 and this has to be 0. And therefore, phi of x, y, and z has no option but being x, y, z, which is the common function that appear everywhere, plus some constant of integration. Why a constant? Well, because when you take the gradient of these, you get the velocity that I gave you up here, yz, xz, xy, in all three directions, regardless of what the value of the constant is. So the constant has to appear there as a potential function to this velocity field or to this vector field. So this is how you do this problem in reverse, for instance. So this is it. I just wanted to introduce the concept of the curl today. Hopefully give a physical interpretation to it, and then just work out a couple of examples forward and reverse to show you how this works. So thank you for your attention, and I'll see you in the next class.